Hi, I'm Megan, and this is Valid Path. Let's get started. So the agenda for today's video is to go over 4 key goals. The first one being to understand the problem statement that we're given. The second is to brainstorm some solutions and look at some pseudocode for our problem statement. The third one is to apply what we brainstormed and try to solve the problem. And the fourth one is, if we can, to improve upon our solution and see if we can make it more efficient. So let's get to understanding the problem statement. Suppose you are given a directed graph with n vertices represented as an edge list, where each vertex is labeled from 0 to n-1 inclusive. Each edge in the graph is represented in a vector of pairs named edges, where edges at I is equal to ui, vi. So ui will denote the start of the edge, and vi denotes the end of the edge. So that will also denote a unidirectional edge between vertex ui and vertex vi. Every vertex pair is connected by at most one edge. So you can see we have a vector of pairs, which is our edgeless representation of the graph. And each pair has a length of 2, which represents one edge, and at most one edge. There are also no self-loops nor parallel edges. So what that means is, if we start to annotate, what a self-loop is, if let's say we have a vertex, 0, we can't loop all the way back to it. So we don't have that in our graph. That's one of our restrictions. And for parallel edges, we also don't have that. So let's say we have 2 vertices, we'll say 0 to 1. And I say 0 to 1 because we start from 0 and we go to n-1 inclusive. So this would be n is equal to 2 for 2 vertices, and then 0 to 2 minus 1, which is n. So those are our labels, inclusive of 1. So let's say we had an edge going from 0 to 1, and we also had the same edge. So it's kind of like parallel lines is what it would look like. So we can't have that as well. Okay, so now our task is to determine if there is a valid path that exists from the given vertex source to the given vertex destination. Return true if a valid path exists and false otherwise. So all we need to do is take a look at the source vertex and the destination vertex and see if there's a valid path that we can determine. And if there is, we return true. So now that we've taken a look at our problem statement, we can go to our constraints. So take a look at the following constraints. It's a really good idea to take a look at the constraints of your problem statement because that could give you a sense of what edge cases you might have and what edge cases you might want to watch out for. So for example, we have in the first constraint n. At minimum, if n stands for nodes, and n does stand for nodes, we will have 2 nodes. So we won't have to focus on an edge case where we could have 1 node or no nodes. We know that there will be at least 2 nodes or 2 vertices. And the vector of pairs that we are given, the edgeless graph representation, will or could be 0. So we might have a graph with no edges. It could be, let's say, 2 vertices and there might not be any edges. So it could be 2 disconnected vertices, which would mean 2 components of the graph. For the third one, that basically just means we have a vector of pairs and each pair has a length of 2. So that doesn't need much saying. For the next one, we just have the edges, ui and vi, so we have the start vertex and the end vertex, and that will be following the labels of the vertices, like 0 to n-1. So if we had, let's say, 3 vertices, it would go from 0 to 3 minus 1, so 0 to 2, and the edges would follow that labeling. And the same thing applies to the source and destination node that we are given, so we can expect that they will also be from 0 to n-1 as per the vertice labeling. And the last 2 are just no duplicate edges, which again means no, let's say, parallel lines. And lastly, we have no self-loops. So ui and vi cannot equal the same thing, and that means we can't have an edge like the following. We have 1, 1, let's say in our vector of pairs. So that pair cannot exist. Okay, so let's go to the test cases. So notice we have 5 test cases. The first one, we have n equals 7. So remember, n stands for our nodes or our vertices. And we have our edgeless graph representation. We have a few edges there. We have 0 to 1, 0 to 2, 1 to 3. And let's go ahead and draw this. So we will have, we'll have 0 to 1. We will have 0 to 2. We will have 1 to 3. We will have 1 to 2, so we will point that over here. We will have 4 to 5, so this will be a separate component of our graph, 4 to 5. And then we will have 4 to 6. So that's all of our edges, and that's our graph. So we have n is equal to 7, so 7 vertices, and 0 to 6, so 0 to n minus 1. So our source is 0, and our destination is 2. And you can see that we actually have 2 paths from 0 to 2. We have, let's do this in orange. We have 0 to 2, so a direct path. And we also have 0 to 1, and then 1 to 2. So although we have 2 paths, we might only end up detecting 1 path, and that would be it for our solution. But regardless, since we have 1 or 2 paths, or how many paths, we are going to return true since a valid path exists. Now for our second test case, we have the same exact graph, but our source vertex is 4 and our destination is 6. And that will also be true because in the second component of our graph over here, we have our source of 4 and our destination of 6. So there is a direct path from 4 to 6. For our third test case, we have essentially the same graph, or pretty much the same graph. But in this case, we have source 0, so that was from the first component over here. And then we have destination 5 from the second component over here. So since the graphs are pretty much disconnected, we have 1 component and 2 component, there is going to be no pathway, no valid path between that source and that destination vertex. So in that case, we would return false, there is no valid path. For the fourth test case, you can see where I'm going with this, that we have 3 edges, 0 to 1, 0 to 2, and 1 to 2. We return false as our output because we have a path from only 0 to 1, hence this edge. It's important to look at the edges and not just, let's say, a visual graph. So now that we've taken a look at how the graphs and the edges might look visually and that valid path might look visually, we can now take a look at the edges we are given to sense that valid path. So we don't have a pathway from 1 to 0, but we do have one from 0 to 1. We have one from 0 to 2 and 1 to 2. Our source is 1, destination 0, so we can't really go backwards, so we return false. For our last test case, we have 4 vertices, but notice the vector of pairs, our edgeless graph representation, is nothing. And if you remember in the constraints, we might be given no edges. So in this case, our graph might look like the following. We have 1, 2, 3, 4, and we have 0, 1, 2, 3. But we have no edges at all. So this is a completely disconnected graph, and we have 4 separate components. So if the source is 1 and the destination is 3, we have no way of getting here because we have no edges, so we return false. So now that we have gone through our test cases for our problem statement, we can go ahead and start brainstorming for our solution. Let's get to brainstorming. Okay, so you can see that we have a graph here from 0 to 6, so that is 7 vertices. So we have n is equal to 7, and 0 to 6 for our labels. As for graph representations, we know that in our problem statement, we are getting a graph representation as an edge list. So there are different ways to represent a graph. We have an edge list, we have an adjacency list, and an adjacency matrix. Those are the main ways we use to represent a graph. And they all have their own advantages and disadvantages. They're very case dependent. But for an edge list, what we could do when it comes to traversing and trying to find a valid path, we can iterate through the edges and look for neighbors. And that might include using a BFS, which is called a breadth first search, which uses a queue. And that also would include checking the nearest neighbors. So for example, if we had a source vertex of 0, we would check the nearest neighbors, so that would be 2 and 1. So that's how BFS kind of starts. So that is an edge list. We would go throughout the entire edge list and just continue checking edges. There's also an adjacency list, which also has its own advantages. And an adjacency list could be more efficient than an edge list in that it could be represented as a map with key value pairs, for example. So we might end up going through the adjacency list, and instead of going through all the edges, we could check neighbors that we actually need instead of, let's say, edges or neighbors that we don't need to check because we know that we don't need those, or we know that those are unnecessary to check. Okay. So again, there are different ways to represent a graph, specifically 3 ways, and all of them are perfectly valid implementations. All of them could be possibly a solution, but in this case, we are given our graph as an edge list, so that is what we are going to try using first. So let's get to solving our problem, but first we need to get to continuing to brainstorm with some pseudocode. Now let's start brainstorming with some pseudocode. So we're going to take this pseudocode step by step, and you can see that we start with creating an empty queue and pushing the source vertex into that queue. And with creating an empty queue, I know that I'm using BFS, breadth first search or breadth first traversal. And that's because I want to check the closest neighbors and continuously do so until I might or I do find the destination. So in my opinion, or in my case, it might help me to create a more efficient solution and find the destination faster than a DFS, breadth first, not breadth, but depth first search. And for a DFS, I would just change that queue to a stack. So they're both valid solutions, but again, they're very case dependent. And in this case, I'm using BFS and a queue because I want to check my closest neighbors instead of possibly going as far down into the graph that I can and ignoring a neighbor that might have been the destination. Okay, so I'm going to have my queue, and I'm also going to have a set to keep track of my visited vertices. And let's say I have a source vertex of 0, and I have a destination vertex of, let's say, 3. Okay. So while the queue is not empty, I only want to go through this while loop, which is kind of like the brain and the logic of my entire program and getting my valid path, if my queue is not empty. Because when my queue is empty, that means that I'm kind of done and I can go to return true or false. So my queue, I'm only really creating a queue because I want to keep track of what vertex to check next. And I want to check its neighbors next, or the vertex in the queue. I want to check that vertex's neighbors next. Okay, so while the queue is not empty, I will go to the queue and store and pop the front element. So if I have 0 in my queue and 0 in my set visited, which is my source vertex, I'm going to store the front element of the queue, which is 0. And let's say I store it, I'll say stored. Right now I have stored is equal to 0. I pop that from the queue and I decide to iterate through the edge list to check for neighbors of that front element. So let's say I have an edge list such as so. I have 0 to 1, I have 1 to 2, and let's also say I have 0 to 2, and how about 0 to 3? Okay. So I have 4 edges, and I want to check if there's a valid path between 0 and 3, and we can see that there is in the edge list. And again, I have my stored vertex 0, which is my source vertex. That's what I'm starting with and focusing on. I want to iterate through the edge list, and check for neighbors of that front element. So I am going to go through this entire edge list and check if, let's say, this stored vertex, our source vertex, matches with this. So that edge in my edge list, the edge dot first, or the first vertex of my edge, needs to match the stored vertex that I have. If it doesn't, then I'm going to move on to the next edge in my edge list. I'm going to go over here. And if it doesn't match, I'm going to go over here and so on. But you can see that at the start of our edge list, 0 matches 0. So the start vertex of our edge in our edge list matches our source vertex, which is stored from the queue. So since it matches, we go to this next if statement. We check if the edge has been visited. So we check, hey, has 1 been visited already? But notice we only have 0 in our visited set. So since 1 has not been visited, we are going to insert 1 into our visited set and push it into queue, right there. And I'm pushing it into the queue because now I want to end up checking 1's neighbors in the edge list. And I'm also going to go through this edge list a lot of times. And that's where we get to possibly improving upon our solution. But right now we're focusing on using an edge list. So after we push it into the queue and the visited set, we're going to move on to the next edge in the edge list. So we're just constantly going through all of these edges. And lastly, we will return true if the destination vertex is in our visited set, because we know if it's in our visited set, then we can visit it. Okay. So now that we've taken a look at pseudocode using an edge list, in other words, the edge list that we've been given to us, the graph representation, what if we could improve upon this? I mean, there are ways to use a different graph representation, for example, such as an adjacency list or an adjacency matrix, as we talked about on the previous slide. And let's get to that and what that might look like. So keep in mind that even though I'm changing to a different graph representation, I'm still traversing through my graph the same way. I'm doing a BFS, a breadth first traversal, or a breadth first search using a queue. I'm checking my closest neighbors and continuously doing that. I'm still creating that empty queue and my visited set. I'm pushing or inserting the source vertex into that queue and set. And so long as my queue is not empty, I will store and pop the front element of that queue. But although these solutions, not these solutions, but these steps are the same, the first one is what kind of pops out. Instead of keeping the edge list that we were given that's kind of passed into our function, we are changing it to an adjacency list. In fact, we are constructing an adjacency list from scratch. We're changing that edge list into a new graph representation. And we're doing this because remember that we have an edge list, and to check all the neighbors for the edge list, we have to go through each edge in the edge list. But for an adjacency list, I might have a map, for example. So I might have, let's say, keys of 0, 1, and 2. And those will be my vertices. And what if I stored my neighbors of each vertex, such as so? I had 1, 2, let's say I had 3, and for 2 I have, let's say, 4. Okay. So you can see that I have my keys here, and then I have my values here, kind of like their own set of integers or other vertices. So just from this adjacency list, if I iterate through them, there is a way just to check the necessary vertices that I need, so the necessary edges. In an edge list, what I might do is check both necessary and unnecessary edges, which could make the solution more inefficient. But an adjacency list could make our solution more efficient, especially in time complexity and runtime. Okay. So that's the only difference in this pseudocode, the fact that we are creating an adjacency list. Our while loop is essentially the same thing. We iterate through the list and we check each neighbor of the front element that we popped from the queue. And we're also storing that front element and popping it from the queue. So since we need to check each neighbor of the front element, we are just going to check if it's been visited. And if it hasn't been visited, we'll insert it into our visited set and push it into our queue because we want to check its neighbors next. Then we will move on to the next neighbor of the stored front element. Lastly, we will return true if the destination vertex can be found in our visited set. So just to reiterate, the only difference is the adjacency list in this second solution. So it does create a better time complexity, which we will go over, but it also is just more efficient in general since we're not iterating through any unnecessary edges and we're not checking, for example, in the edge list, we had to check if the start vertex of the edge matched the stored and front element of the queue. So we had to check, let's say, if our stored variable or stored vertex was 0. And then we had to check the edge, 0 to 1. Let's say we had 1 to 2. We had to check this and we had to check this. But for an adjacency list, we would only have to check this and then its neighbors. So that makes it a lot better. So now we can get into solving and applying the pseudocode as well as the two graph representations into our solution. And then we can look at how one is efficient and one is possibly more inefficient compared to the other. Okay, so we looked at two different types of pseudocode. So by types, I mean different graph representations and ways of finding the valid path. One is more inefficient and one is more efficient, undoubtedly. So let's start coding, but let's focus on the first slide we looked at, which is keeping the edge list. So what happens if we just keep the edge list and don't focus on any other graph representation, no converting or anything like that? So we know we are performing a BFS, and I also want to write the goal. So we want to find the valid path from source to destination, just as a reminder because our goal is just the one thing we should be focusing on. And to find the valid path, I want to use a BFS because I want to check the neighbors, all neighbors possible, and continue checking the neighbors until I find the destination. I don't want to go too deep in the graph and possibly miss something that I didn't want to miss. And for that reason, I'm going to create a queue. So I'm going to do queue of type int. Just going to call it queue. And if you remember from the pseudocode, what I'm going to do is push in the source vertex. So that's the first neighbors that I want to check. I want to check the neighbors of the source vertex first. And I also created a set. In this case, I'm going to create an unordered set of type int, and I'm going to call it visited. So this set just represents all of the visited vertices so far. And I have it as unordered, which is backed up by a hash set, because I don't really care if my visited nodes or visited vertices are in any particular order. I just want to make sure in the end if that destination vertex is in the set or if it isn't. So let's continue. And what we did before was we took this and we inserted the source into our set. So now we have two containers. We have a queue and we have a set of visited vertices. The source is in both containers. Next, what we want to do is kind of create a variable, so maybe a current variable in current. And we want to use that to keep track of what vertex we're at. So when we're popping and pushing from the queue, how are we going to keep track of what vertex we're at? We want to store it. And remember, while the queue is not empty, oops, let's fix that. Okay. So while the queue is not empty, I will continue with my iteration and checking neighbors and edges and so on. So the first thing that I need to do is set my current vertex to something so that I can continue checking my neighbors or start checking my neighbors of that current vertex. And to do that, I'm taking it from the front of the queue, and then I'm going to pop that off as per our pseudocode. Once I've done that, I have my current vertex, and now I want to check the edges in my edge list and look for a match. So let's say my current vertex is a source of 0. I want to go through the edge list and check if any of the starting vertices in any of the edges match that 0. And if it does, I want to push it into visited, but first check if it has been visited. And by checking if it has been visited, what I mean is checking the end vertex of that edge, not the start vertex. So I have my current vertex stored, and what I'm going to do is a for each loop. So for edge in edges, let's do for auto edge. Let's say if cur is not equal to edges dot first, and let's do using namespace std up here and include utility as well. Okay, so if cur is not equal to edges dot first, seems to be a problem for current variable. Okay, edge dot first. Then what I'm going to do is continue in my if statement. Right. So what I'm doing is I'm looking at the first vertex in my edge list, and I'm checking if it's equal to my current stored vertex. And if it's not, then I want to continue on to the next edge. But what if it is a match? If it is a match, then what I want to do is I want to check if visited.count, and I'm using count as a way to check. The count function or method really just returns 0 or 1, or true or false if the vertex has been found. So I want to check if the edge.second, so the end vertex of that edge, is in my visited set, or in other words, has been visited already. And what that does, it helps me avoid visiting anything again or continuing in cycles if our graph has a cycle. Okay, so visited.count, edge.second, and I want to set that equal to 0 because that means false. So if our edge.second, the end vertex of our edge, has not been found, then what I want to do is I can push that into my queue, so edge.second, and I also want to insert that into my set named visited. And that's because I have visited it now. And a small optimization that we can do is we can check if we reached the destination early. So if we reached it early, then what I could do, if cur is equal to destination, instead of cur, what I mean is edge.second is equal to the destination, then I'm going to go ahead and return true. And if it hasn't reached the destination, so not only does this check if the destination has been reached early, but it also checks if it's been reached at all. So reached destination. If that has not been reached, then we will return false by default. And this is our solution. We can go ahead and test it out, but what we're going to do first is create the next solution, which was the second slide of the pseudocode, using an adjacency list, and then we are going to compare the two first. Okay, and to go through this as well, let's go through one of the test cases. So let's go through sample case 1. We have n is equal to 7, and we have, actually, let's make this a little bit shorter. So we will do n is equal to 3, and our edge list will be 0 to 1, and then we will have 0 to 2, and let's have 1 to 2. Okay. My source is going to be 0, and my destination is going to be, let's say, 2. Okay, so that will be this second edge here. Okay, so I have 3 vertices, 0 to 2 inclusive. I have a source of 0 and a destination of 2. I'm going to start with an empty queue. So my queue is going to be empty, and it's going to have the source vertex pushed in. So Q is going to have 0. And then my visited set, visited, is also going to have 0 in there because we are starting with the source vertex of 0. Then I have my current vertex, which I'm storing based on the queue. So current will be set to 0 first, which is the source vertex. My queue is not empty, so it's true, because I end up popping the source vertex after checking if my queue is empty, which it isn't. Then I'm going to do a for each loop, just for ease is what I did, and I'm checking through the edge list that was passed in, so the graph representation that we were given. So I might have, let's see, all of these edges. Let's copy and paste this over here. So I have cur is equal to 0, and I'm going through this edge list, and I'm looking if cur is equal to edge.first. And over here it is. We have a match. So we're going to go to this next if statement, and we are going to check if edge.second has been visited, which it has not. One has not been visited and is not in our visited set. The only thing in our visited set so far is our source vertex. And we also know that it has not reached the destination early because our destination is 2 and not 1. So we're going to push it into our queue. So queue will now have 1, and 0 was popped out after we checked if the queue was empty in the while loop. And then we are going to insert it into our visited set. So we have 0 and 1. All right. So we are going to continue into our edge list since we found a match. So we go into the next edge. We check 0, 2. We still have current is equal to 0. And that's another match. So 2 is actually our destination. So this ends up checking out. We reach this if statement. We check if 2 is visited, which it is not. But we don't even need to insert it into our visited set. We don't need to push it into our queue or anything of that sort. We just found a valid path immediately, and we returned true. So that was our small optimization that helped a lot for just identifying an early destination or an early valid path, instead of continuously going through all of the edges and pushing and inserting into our visited set. So we would have reached a destination here and then returned true. So that is our solution using the edge list that is passed in. And next we are going to go over a solution using an adjacency list before we compare the two. Okay, so now that we have done our first solution using an edge list, let's see what happens when we convert our edge list into an adjacency list. So I'm going to create the same function, but in this case, I'm going to call it valid path improve, since I believe this will be a lot more efficient given the fact that we're not checking unnecessary edges as well as necessary edges. In an adjacency list, we will be having, let's say, an unordered map and then an unordered set given to each key, and that unordered set will only have the neighbors of each key, and the key will represent a vertex. So I only need to check the neighbors of a vertex, not go all the way down and check all of the edges. So I'm going to have bool valid path improve. I'm going to have int number vertices, have my vector of pairs. So vector pair, I'm going to have pair of integers, that's called edges, which is the edge list passed in, and then I'm going to have int source, int destination. This needs one more bracket. Okay. All right, so the good thing is that if you remember in the second slide of the pseudocode is nothing really changed with the way we approach the problem besides constructing an adjacency list for the sake of efficiency. We still used a BFS to find a valid path, and we were still checking the neighbors, which is good because really not much will change in this code. The only thing that will change in the start of everything is creating an adjacency list. So let's start with that. And you remember that we had an unordered map, or we said we would have a map for the adjacency list, and the key will be of type int, where the key will represent a vertex. And for the value, I'm going to have an unordered set of type int as well. And I'm going to call this adjacency list. All right, so what this kind of looks like is, let's say I have, let's do this. Let's say I have a key, which is a vertex of 0, and its neighbors will be an unordered set or a set. And let's say its neighbors are 0, the key is 0, and then the neighbors are 1 and 2, for example. So I'm not going to have an entire edge list. Instead, I'm going to have a map with a key and value pair. And that's how I'm going to be checking for the neighbors in a much better way compared to the edge list. And once I've started to initialize my adjacency list, the one thing I want to do is make sure I've got the same edges from the edge list into the adjacency list. So what I'm going to be doing is kind of reconstructing the edge list that I was given. So I'm going to use a for each loop. So I'm going to have for auto e in, let's say, edges. And then I'm going to do adjacency list. And the cool thing about this is that I can actually access the key and add a value to it. So I'm going to do e.first, insert e.second. So what this does is this creates a key, which is the start vertex in an edge in the edge list, and then it gives it a value, which is the end vertex of that edge. So that's really how I create my adjacency list. And now my adjacency list, it iterates through all of the edges in the edge list and creates a whole new structure for my graph. And after this, it's essentially the same. I have a BFS traversal, so I'm using a Q again. So I'm going to do int Q, type int, oh no, int Q. I think I did this, yes. All right, so I have Q int Q, and I push in my source vertex. And after that, I'm going to create my unordered set. So same thing of integers. I'm going to call this visited, my set of visited vertices. And I'm going to insert my source into this. Okay. So I have two containers once again, and I have my set of visited nodes, visited vertices, and I also have a queue with the source vertex first. What I want to do next is iterate through the adjacency list. So it's pretty similar to what we did over here, where we iterated through all of the edges in the edge list. But for our adjacency list, we're only going to iterate through what we need to get, so the neighbors instead of all the edges. So what I'm going to do is another for each loop. I'm going to do auto, let's say v, in adjacency list. Actually, before we do this for each loop, what we also want to do is create a current variable to store the first or front element from our queue. So we'll do that first. We will also do a while loop, just like before. So while q is not empty, we're going to set cur to q.front and then pop that off. So as you can see, it's the same thing we did over here. We had our current variable to store the vertex, we had our while loop, and then we set it equal to the front element in the queue because we were going to check the neighbors of that current vertex, which was previously the front of the queue before we popped it off. And instead of doing for auto edge, what we are going to do is after this, we're going to do for auto, let's say v in adjacency list. Remember, I have my current vertex, so I want to check the neighbors. Instead of v, I will say neighbor. For each neighbor of that current vertex in my adjacency list, I'm going to check if it has been visited. So if visited.count neighbor is equal to 0, so this means it's not visited, I'm going to push it into the queue to check its neighbors. And I'm also going to mark it as visited. And again, we have a small optimization that we can do if we reach the destination early. And we can check if the neighbor has been unvisited. So if it hasn't been visited, we can do if neighbor is equal to the destination. Return true. And if it hasn't, that not only checks for an early arrival at our destination, but also if we've reached our destination, we can go over here at the end of our while loop and return false by default again. So let's go through this one more time with one of these sample test cases. So let's say I have, start here. Let's do the same test case that we did over here. So we have n is equal to 3, so 3 vertices, and I have edges, 3 edges, 0 to 1, 0 to 2, and 1 to 2. And I have the vertices 0 to 2. My source is 0 and my destination is 2. So what I start with is I create an unordered map with values of an unordered set, and I call that adjacency list, and I construct my adjacency list from the passed in or given edge list. I give each key in my adjacency list a value, which is the second vertex in the edge list. Then I do a normal BFS using a queue. I also have my visited set over here, the current vertex that I'm at for storage purposes and continuing to traverse through my adjacency list. I check the neighbors of that current vertex and nothing else. I don't check multiple edges like I did in the edge list. I check if the neighbor has been visited, and if it has not been visited, I check, hey, have we reached the destination early? Is that neighbor our destination by any chance? And if it is, we got lucky and we return true. If it isn't, we continue pushing it into visited and the queue. So if we start with a source of 0, then our queue is going to have 0. And our visited set is also going to have 0. And our adjacency list, let's call this adjacency list. Adjacency list is going to look something like this, where I have my first key, which is 0, and that has the following set, the following unordered set of 1 and 2. And then I have, let's see, all right, we'll keep that. Then I have my next key, which will be, let's see, 1, and that will have, let's do 1, that will have the neighbor of 2. So 0 has 2 neighbors in the edge list, 1 and 2, and then 1 has 1 neighbor in the edge list, which is 2. So that's what our adjacency list looks like. We have a key, and then we have values represented as an unordered set of integers, so our vertices. So after that, we are going to set our current variable, or the current vertex that we're at, equal to 0. So that is our source vertex right here. And we're going to our destination of 2. So just like before, I'm just going to add a reminder of our goal. Find a valid path between source and destination vertex. So when it comes to coding, I really like reminding myself of the overall goal, maybe in a comment above where I'm coding or around where I'm coding, so I can reference it if I ever find myself getting too lost in the code. So this really helps me, and I guarantee that it might help you as well. Okay. So I have current is equal to 0, and I have while my queue is not empty, my current, this is where it actually equals 0. This is just the initializing the current and making it exist. So it equals 0 because that's the front of the queue over here, and that's where I pop off 0 from the queue. And I go in my for each loop and I check the neighbors of the current vertex in the adjacency list. So if current equals 0, then I go back up here and I check the neighbors. I check 1. I say, is 1 visited? And it's not. So I check if that's the destination, and it also is not the destination. The destination is 2. So what I do is I push 1 into the queue and I insert it into the visited set. So now my visited set has 1 and my queue has 1. Next, I'm going to check the next neighbor of 0 since current is still equal to 0, which ends up being 2. But our destination has been reached early again. So right here, I am going to return true, and that's it. If that wasn't our destination, or if we didn't have our destination in our adjacency list, I would return false by default, and this would have never been reached. Okay, so we've reached our destination early. We didn't need to put the vertex 2 in our visited set or our queue because we didn't need to continue going through our visited set, checking them, or going to check more neighbors of the vertices in our queue. We just stopped there, we found a valid path, and we are good to go. So now that I have an improvement of our previous valid path solution using an adjacency list, and my old valid path solution using an edge list, we can go ahead and test these out real quick with an int main. And remember that both of my functions, I'm being given a vector of pairs, type int, and we will call this graph1. And what I am going to do is I'm going to do graph1.insert. I will do, let's say, insert, All right, so again, as I said, we have our two solutions, so we will go ahead and test it in main. And remember that we are passing in a vector of pairs, pair, type int, and we will call that graph1. And that is our edge list, or our graph representation that we will be given. Then what I want to do is insert some edges into that edge list. So I'm going to do graph1, and it's a vector, so I'm doing pushback. And I will do pair, where they are both integers. And my first pair, let's say, is 0, 1. And let's just write these again. And I'm going to say another pair is 0 to 2, and another one is 1 to 2. And what I want to do is I'm going to cout bool alpha. And as you can see, the functions I created, the solutions are of type bool. And that's going to return 0 or 1. I want to convert that to true or false, so I'm just using bool alpha over here. So it's a nice little trick. And over here, I'm going to call valid path. So this is the one with the edge list. And first, I'm going to pass in, let's see, we pass in the number of vertices. So we will pass in 3. Then we will pass in the graph1 representation. Then we'll pass in the source, and let's say a destination of 2. So this is, I believe this is the test case we used before to go through these, right? We had 3 edges, 0, 1, 0, 2, 1, 2. We had 3 vertices, source 0, and destination 2, which is the same thing. Okay, so what this should return is true because this is our valid path. All right, so what we can go ahead and do is test this out. But before we do that, I am going to write the edge list representation, because I'm going to write the same thing for my adjacency list, and I want to be able to differentiate between the two. Okay, let's pull this up. All right, so let's just reformat that a little bit. But you can still see that it returned true. There is a valid path, which is very good. And now we can do the same thing. So I am going to pass in the same graph, the same edge list, and I'm going to say adjacency list representation. And this function is valid path improve, and this should also return true. So we will just run that. Let's do another endl here. Okay. Okay, awesome. So they both return true. They both found a valid path between 0 and 2, 0 the source and 2 the destination, and that is true over here. So we can also go through one of these sample test cases as well. Let's try, let's see, a completely disconnected graph. well, not a completely disconnected graph, but we'll have two components of a graph, and we will check if one component from the first, or one vertex from the first component, can have a valid path to another vertex in the second component, which is impossible because they're different components, so they're not connected. So I'm going to say n is equal to 7 for both, 7 vertices. For my edges, I'm going to have 0, 1, 0, 2, 1, 3. I'm going to have 1, 2, 4, 5, and then 4, 6. And then that should be it. So I have my pairs 0, 1, 0, 2, 1, 3, 1, 2, 4, 5, and 4, 6. Get rid of this. My source vertex is going to be 0, and my destination is going to be 5. Change our destination. And what this should return, as said in example 3, is false, because we have one component, let's say over here, and another one over here, and we can't go from one component to the other. There's no real path. So both of these should return false. Let's go ahead and run this. Awesome. So they both return false, and we have two working solutions, although one is more efficient than the other. And we'll see why one is more efficient than the other. We know when we use the edge list that was passed in or given to us, we're going through all of the edges and checking unnecessary edges as well. For the adjacency list, we are not doing that. We're only checking the edges that we need to, or the neighbors that we need to. So the time complexity of our adjacency list will be O of v plus e. So the for loop is never actually going to go over the number of edges. It's actually only, in the worst case, going to be equal to the number of edges. Okay. So if the time complexity for the adjacency list is O of v plus e, then the time complexity for our edge list solution is O of v times e. And there will be an O of v plus v times e over here, but since it's big O, we will cancel this out. And that extra v was just for the number of times our while loop iterates. What this means, O of v times e, is the number of while loops. So the while loop is, or the for loop is iterating e times, and the while loop is iterating v times. So the while loop impacts the for loop, and for the for loop, we are going through all the edges, and that takes a considerable amount of time, meaning the time complexity is far worse than using an adjacency list. So that is both of our solutions. One has a time complexity of O of v times e, and the other has a time complexity of O of v plus e. So you can see that the best solution is the one using the adjacency list, and the worst solution is the one using the edge list. And that sums up today's problem. So I hope you enjoyed this video, and I will see you next time.